Okay, section 10.2. We're now going to be talking about rational exponents, right? Now you remember the word rational. The word rational in math means fractions. So I know we just spent a whole chapter, chapter 7, on fractions, and you're probably sick of those by now. But, you know, fractions are everywhere. We do have to deal with them. So here it's the exponents that are going to be fractions, right? So you know, for example, what x squared means. It just means you take x times x, right? And you know what, 3 to the 4 means, right? It just means 3 times 3 times 3 times 3, which is also 81, right? But you might not know what 3 to the 1/2 means. So what happens when the exponent is a fraction? That's what we mean by a rational exponent. Yeah, so this is probably something you haven't seen before, right? Because it kind of doesn't make sense. I mean, how can I take 3, the number of times I have to multiply 3 by itself, right? It's 1/2 time, right? So be careful. This is not half of 3. This is not 3 times 1/2, right? Yeah, I should use parentheses to indicate multiply, right? Here's the exponent that's 1/2. Okay. So let's think about this. Let's do this example here. If I have, let's say, let's look at 9 to the 1/2. Or well, let's make it 25. Right, so 25 to the 1/2, right? So this is just some number, and it's some number that I can get rid of the 1/2 if I just multiply 1/2 times 2, right? Half of 2 is 2 divided by 2, right? Which is just 1. So I can make this an exponent of 1 as long as I multiply the 1/2 times 2, right? Oh, sorry. Yeah, this 2 should not be here, right? It's just x for now. But yeah, so what I want to do is if I raise the left side to the power 2, I have to do the same thing to the right side. I can't do to one side and not do it to the other side, right? So now we have a 2 there, right? So by the rules of exponents, right, the left side is just 25 to the power 1, right? 1/2 times 2 is 1. And the right side is x squared. Okay, so what number to the power 2, what number squared is 25? Well, there's actually 2 answers to this, but the obvious one, I think most of you are probably screaming out, it's got to be 5, right? 5 times 5 is 25. And sure enough, right, this is just 5 squared. So that x is just 5, which is also the square root of 25. So now this gives us a pretty good indication of what this is actually. It's just the square root of 25, right? So now I know what it means to raise an to have a power of 1/2. Let me write it way over here. Let me do it here for now, right? If I take some number and I raise it to the 1/2, all I'm doing is taking the square root of that number. In other words, this is just another way to write the square root, right? So in fact, here, if I have 3 to the 1/2, now we can answer that question. That's just the square root of 3. Right, and the square root of 3 is some decimal, right? It's approximately 1.732, and so on. But we're not going to worry about that. We're just going to leave it as the square root of 3, right? It's think of this as like in lowest terms. This is the simplest we can write it, without writing it as a decimal. Okay, so we can play the same game with an exponent of, say, 1/3, right? If I have, let's say, 8 to the power 1/3, right? Well, this is just going to be some number, let's call it x, that if I raise it to the 3rd power, I get 8, right? And, if you take 2 times 2 times 2, or 2 to the 3rd power, you get 8. So this x here has to be 2. Which is the same thing as the cube root of 8. So 8 to the 1/3 is really just the cube root of 8. Right. Whereas 3 to the 1/2 is the square root. You know, you can put the 2 here, but that's optional. All right. But when it's the cube root, you have to write the 3, because if you don't write the 3 here, it's the square root of 8, which is not the cube root of 8. Okay. So yeah, I think we have the idea now. Now we can write the rule here. If I have some number, I'll just call it a, and I raise it to a power of 1 over n, so n is the denominator. The denominator of the exponent is just the index, or the root. So this is the nth root of a. Okay. So that's what happens when you have a rational exponent. You turn it into a radical, and then it's easier to deal with. It's easier to evaluate, right? Okay. So, yeah. So let's do another example. Suppose we want to convert to a radical. Right. We're going to do a couple of these. I'll call this example 1. Convert to a radical. So suppose I have, let's just do 19 to the power 1 over 3. Right. Well, here n is 3, so that should be the cube root of 19. Okay, and that's it. That's all you have to do. That's the answer. Right. Just convert to a radical. Again, we're not going to try to simplify this. We're not going to convert it into a decimal or anything. We're just going to leave it as the cube root of 19. Okay. So let's do another one. So convert to a radical. How about if I just have, let's say, w to the power 2 over 5. So my 2 is a little small there. Let me try it again, right? 2 over 5. So here, this is interesting because this exponent here at the top is just 1 over n. So the denominator is 5, the n is 5, but we have a numerator of 2, not 1. So this is a little trickier. But here's what you can do, right? You can rewrite 2 over 5 as 1 over 5, right, times 2, right, 2 over 1. Right? And if I do that, remember, I can also split that up as the exponent, right? In other words, this is just w to the 1/5, all raised to the power 2, because you would multiply 1/5 times 2, right? Now, if you look at what's inside here, the w to the 1/5 is exactly just, right, so a is w and n is 5. So this is the 5th root of w here. And that's what's in the parentheses, right? This is the 5th root of w. But then don't forget we have to square it, because that's the 2 on the outside, right? So that's what this is, right? This is just the 5th root of w squared. And as long as your w is not negative, you can also write it as the 5th root of w squared, right? So either way works. We're not going to be picky about that. Technically, you do have to be careful because this is not always true. But let's write the rule where it is true. So the rule, and maybe I'll go back up here now. So getting rid of some of the clutter here. Yeah, so we can amend this rule here and show you what happens when you have a numerator that's not 1, right? So the new rule will just be this. If I have a to the power m over n, right? So m is the numerator, n is the denominator. We can write this as the nth root of a, and then take that whole thing to the power m. And this is also going to be the nth root of a to the m, as long as this is a real number, right? And so, in other words, if a is positive, then this is always true. Right? So in other words, it doesn't matter whether the exponent is underneath the radical here or if it's outside the radical here. Okay. Okay. So that's the idea, right? And so this is just a special case where m is 1. But if m is not 1, then the numerator becomes the exponent, the denominator becomes the index. Right? So yeah, let's do another one. So example 3. Again, convert to a radical. Suppose I have 16 to the power negative 1/2. So there's no negative sign in the rule here, right? It's not a to the negative m over n. It's positive. So what does that mean? How can you have a negative 1/2 for an exponent? Well, how can you have a negative exponent, right? This is nothing new. I'm going to scroll down for now, but this is something we've done a long time ago. If I have, let's say, a to the negative 2, you should know what that is, right? Remember, it's not negative a squared. When the exponent is negative, it means you take the reciprocal. It's 1 over a squared, right? In general, if you have a to the negative n, this is 1 over a to the n, right? So this was a rule that we had way back in chapter 5. So you might have to go all the way back to chapter 5 to review that, but that's all it is. When you have a negative exponent, it means you just take the reciprocal, right? And if it's in the denominator, remember that, if you have, let's say, 1 over a to the negative 2, then when you flip it over, you get a to the positive 2 in the numerator, right? But back to this problem, 16 to the negative 1/2, right? So what are we supposed to do with that? Well, let's start by just changing this to a positive exponent. How do you change a negative exponent to a positive? Well, we did it down here, right? You take the reciprocal. So this is just going to be 1 over 16 to the positive 1/2. Okay, so I got rid of the negative exponent by taking the reciprocal, right? Flip it over, right? Now we don't have the negative anymore. What's 16 to the 1/2? So that to answer that question, we go back to this up here, right? N is 2, so it's the square root, and a is 16, right? So this is still in the denominator. It's going to be 1 over, right, the square root. In fact, you can put a 2 here, although that's optional, of the number 16. Okay. And in fact, you should know what the square root of 16 is. Right? It's 4. So this is just 1 over 4. Right? So 16 to the negative 1/2 is not negative 4, right? It's 1 over 4. Let me try that again. Yep. There we go, right? So yeah, the same rules apply when you have a negative exponent. It just means you take the reciprocal, flip it over. And so it doesn't matter whether it's a negative of a fraction or negative of a whole number. You just have to flip it over, right? It doesn't mean it's negative. Okay. I guess let's do a few more. We up to example 4. So why don't we go the other way? Why don't we convert to an exponent? Right. So what if I have, let's say, the cube root of p to the 5? So what's the cube root of p to the 5 if we were to write that with an exponent? Well, let's go back to the original rule here, right? Here, the n, the index, is 3, and the m, the exponent, is 5. Okay, so I know it's way up here, so let me rewrite the rule down here so we can deal with it. Right here, the n is the index that's on the outside, and the It's an a here. So a is p. And the exponent is m. So this is the same thing as a to the power m over n. Right? So I just wrote that from up here just backwards, just the other way. Right? And by the way, I've been writing fractions this way, like 1 over 4, right? You notice I've never written fractions like this, and I would highly discourage you from doing this, right? This is a very bad way to write a fraction. I know that in the old days, some of you may remember writing fractions this way, but it's just poor form. It's not the way you want to write fractions, right? We have not been doing this up till now. That said, because the exponent is a tiny number, right? And the exponent is a little bit smaller, it becomes a little more, well, the numbers become very tiny here. And when you have two of them in the exponent, because it's a fraction, very often the book will just write it this way to make the numbers bigger. So what I said earlier, that you should not write a fraction like this, well, that's true if it's not in the exponent. You should not do that, right? You should write it instead this way here. But when it's a fraction, because this is so tiny and it's hard to read, it might be easier to write it this way. And that's what the book does. So when you see this in the book, you'll see it written this way. I'm pretty sure Connect Math would probably do the same thing, although they might write it this way on Connect Math. I don't remember. So just be aware that either way is fine. But in general, you should not write fractions this way. Only when they're exponents does it kind of make sense to do that, right? Right. So yeah. So here, the a is p, the m is 5, and the n is 3. So this, according to this rule here, this should just be 3 to what power? So here's where you have to be careful, right? Because you have two numbers, 3 and 5. Right? So is it 5 over 3 or is it 3 over 5? What's the numerator? What's the denominator, right? The exponent is always the numerator. It's always the thing on top. So here the exponent is 5. That's the numerator. The denominator here, I should use a different color, right? The denominator here, the n, is the root, the index. So that goes on the outside. So the outside number is 3. That goes in the denominator. Oops. That goes in the denominator. So you can see, that, again, on some of your screens, this might be really tiny here. Hang on. This might be really tiny. So if it helps, you're allowed to write this as p to the power 5 over 3. So now you see why we use, or why the book uses this instead of this. Because this exponent here, I'm sure, is very hard to read. It is for me, because it's very tiny. So just keep that in mind. But I'll accept either. And, you know, if you have to write it with just write it bigger, right? So that's a little better than this. Okay. But be careful you don't get it mixed up. In other words, don't write it as, this is not the same thing as p to the 3 over 5. Right. What would that be? What would p to the 3 over 5 be? Well, now the 5 is the denominator. That becomes the root, the index, right? And then the 3 is the numerator. That becomes the exponent. So p to the 3 over 5 is really the fifth root of p to the 3, right? Which is not the same as the cube root of p to the 5, right? So yes, be careful you don't flip your fraction, because that would be essentially switching the m and the n around, right? You don't want to switch these around, because usually that gives you something different. Okay. Okay, so let's do another example. Let's just go back to numbers. So let's evaluate. How about negative of negative 8 to the 1/3? Yeah, tricky, because you're used to thinking, well, a negative times a negative is positive, right? can we really do that here? Right? Can we do that here? Can we make this a positive? So, right, before we just do that instinctively, let's see what we're doing here. We're taking the negative is on the outside, and now we're taking to the power 1/3. Remember, when the denominator is 3, it means the index is 3. It's the cube root of -8. To the 1, if you will, because the numerator is 1. The exponent is also 1. That's the m, right? But because it's 8 to the 1, or -8 to the 1, we don't need to write the 1, unless you want to, right? So now, what's the cube root of -8? Well, it should be -2, right? Because -2 times -2 times -2 is -8. And now we have -2, which is indeed +2. So the answer is +2. And so yes, here the negative signs cancel. Okay. But you have to go through this to make sure you understand that, right? Go through it step by step. Don't just assume that you can cancel these negatives here, right? So let's do another example. Let's evaluate. Let's do negative. How about -25 to the power 1/2? Okay, so instinctively you want to say, well, look, I know the power 1/2 is just the square root, so a negative times so it should be the square root of 25, which is 5, right? So your instinct would tell you 5. Unfortunately, your instinct is wrong here. It's not 5. Oops. So what went wrong here? Why did that work here and this is not going to work here? Well, remember what the power 1/2, right? The index is 2, so that means this is going to be the square root of -25 to the 1, right? And it's true that the square root of 25, the square root of 25, you all know is 5. And if I have the negative square root of 25, well, that would just be -5. But remember, this thing here, the square root of -25, because the index is even, and you're taking the square root of a negative number, this thing is not a real number. Oops. This is not a real number. Right? It's an imaginary number. Right? Now, you might think, well, okay, so it's a negative imaginary number, and you can think of it that way if you want. But for our purposes right now, this is not a real number, right? It's not -5. It's not +5 either. It's not 5, it's not -5, it's none of those. It's not a real number. It's an imaginary number. Okay? So, yeah, so I think I asked the question, and I hope you thought about this. Why did we get a perfectly good answer here, a perfectly good real number for this example, for example 5, right? And then we got this nonsense, this imaginary number for example 6. And yeah, I hope you realize it has to do with the index, right? The index here was an even number. Here was an odd number, right? And if you look in the denominator, here the denominator was an odd number, and here it was an even number, and that makes all the difference in the world, right? With cube roots, you never have an issue. You're never going to get an imaginary number when you have a cube root, or a fifth root, or a seventh root, right? When the index is odd. But when you have a square root, or a fourth root, or a sixth root, when the index is even, that's when you get imaginary numbers, right? Or in particular, when you have the square root of a negative number, right? So you have this negative sign inside the square root. That's what made this imaginary. Okay, I hope that helps. Okay, so let's keep going. Let's do some more. Practice makes perfect, right? So, example 7. Yeah, let's go back the other way. Let's convert to a radical. So we're going to have an exponent. Let's just do 2x minus y to the power 3 over 2. Okay. So we have a fractional exponent, a rational exponent, and we want to convert this into a radical symbol, right? Well, again, you might have forgotten by now, but eventually this will be second nature to you. You will remember that the numerator is the power, the denominator is the index. Since the denominator is 2, this is going to be a square root, not a cube root, right? So this is going to be, oops, I should use yellow here. This is going to be the square root of, well, the a here is everything, 2x minus y in parentheses. And the exponent, the power, is the 3. The numerator is always the exponent, 3. Okay. And you can leave it like this. Just keep in mind, though, that depending on Connect Math, right, you really shouldn't put a 2 here because it's the square root. So you should just write 2x minus y to the 3 under the radical symbol, right? So again, if you put a 2 there, I don't mind, right? I'll mark it as correct. It's just redundant, right? This 2 is not necessary. Because it's already the square root, we don't need to write it. Okay. If it were a cube root, then you would have to put the 3 there. But remember, the 3 is the numerator, not the denominator. So that should not be a 3 there. That should be either a 2 or just leave it blank. Right? And remember, the 3 doesn't have to be on the inside. It could also be on the outside. You can just take the square root of 2x minus y and then take the whole thing to the third. And effectively, they're the same thing. We're assuming that x and y are, or the 2x minus y comes out to a positive expression. So in that case, either way is fine. So both ways are correct here. Okay, let's do another one. I guess this will be example 8, which I'll do down here. Yeah, how about if we convert to an exponent? Convert to technically a rational exponent, but an exponent. Okay. So suppose I have, let's do the square root of w divided by the cube root of p squared. Okay, so we want to rewrite this with exponents rather than radical symbols. Right. So there's really two things we have to do here. We have to look at the numerator, right? Remember, not the numerator of the exponent. That's the whole idea. We want exponents that might be fractions here, right? So the square root of w, hopefully you remember that that's just w, right, to the 1 over 2. Again, they're not going to write the 1 and the 2 here because they're understood, right? We're just lazy and we don't write them. But yes, this is w to the 1 over 2. Or if you prefer, you can write it as w to the 1 over 2. I'll accept either. Now, what about the denominator, right? The denominator, the index is 3, so that should be the denominator, something over 3. And the exponent is the 2, that should be in the numerator, right? So p to the 2/3. Or, if you prefer, you can write it as p to the 2 over 3, right? So either way is fine. These are now exponents. So I hope that helps. So at this point, I should say, well, you know what? Let's do one more example. Then we'll move on to what we can do. The rules for exponents applies even when the exponents are fractions. So we'll get to that next. But let's do one more example here. Example 9. Let's just do an evaluate because these sometimes can be tricky, right? So let's evaluate. Let's do 81 to the negative 3 over 4. Okay, again, the book would write it this way. Personally, I would write it this way. But yeah, same thing, right? So let's evaluate that, right? What could this be here? Okay, so first of all, we have a negative exponent, right? And we dealt with this earlier. Should I remind you? Wait, where? Oh, I thought we'd, oh yeah, here we go. Yep, way up here. Oops. We had this negative exponent, and remember that just means you take the reciprocal. So the first thing we should do here is change this to a positive 3/4, and to do that, we put it in the denominator. So this is 1 over 81 to the power 3/4. Makes sense? Okay. Right, now we're still not done because we still have to figure out what's 81 to the 3/4. Well, the denominator is 4, so that's the index, that's the root. So we still have 1 over the 4th root, right? Not the cube root, right? 3 is going to be the exponent. It's the 4th root of 81 to the power 3. Okay, now what's 81 times 81 times 81? Yeah, I don't know either, right? I mean, of course, your calculator can tell you that pretty quickly. But I don't have a calculator handy right now, so I'm gonna show you a better way to do this. Remember what I said earlier, that this 3 here can go on the outside? So I would prefer to write it this way. So we still have the 4th root of 81, but now all of that gets raised to the power 3, right? So effectively, these are the same things, right? It doesn't matter whether the 3 is on the outside or the inside. So why is this better? Because I can think of the 4th root of 81 now. Or I can try to figure it out, right? It's 81, if you remember, is 3 times 3 times 3 times 3. It's 3 to the 4th power. So the 4th root of 81 is just 3. Okay, so that's what's, you're taking the 4th, well, okay, hang on. I got to do it this way, right? This is going to be 1 over, the 4th root of 81 is 3, and now we still have this exponent of 3 here, right? The 3 was just what's in the parentheses here. All right, so what's 3 to the 3rd? 3 times 3 times 3 is 27. So there's our final answer, right? This is just 1 over 27. Make sense? Okay, so this is the way I would think to do it. Of course, going back to this, you could do it this way too. But here, you're probably going to have to use your calculator, right? So let's do 81 to the power 3. What's 81 times 81 times 81? It's a big number. It's a pretty big number here, right? It's, it's going to be, right, so 1 over the 4th root of this really big number, 531,000, that's a 1, 531,441, right? So now, what's the 4th root of 531,441? There's no way I expect you to know that because I don't know that. That's a really big number, and to take the 4th root, it's just kind of crazy to try to do that by hand, right? On the other hand, your calculator, depending on what type of calculator you have, you might have to look for the correct button here. Right? If you have a basic calculator, you might have a button that says x to the y. If you see that, then it's probably the shift key that will give you the y-th root of x here. So, right, but remember the 4th root is also to the power 1/4. So you can use this button. You just have to do 531,441 raised to the power 1/4. So that's how you can effectively do the 4th root of a number. So I'm going to do that on my calculator here. I'm going to raise it to the power 0.25, and you end up with, well, no surprise, 27 in the denominator, right? So 1 over 27. So you get the same answer, but you can see in this way you have to deal with bigger numbers and then the fourth root of bigger numbers, and effectively this forces you to use your calculator. Whereas by doing it this way here, right, by doing it this way, at no point did I need a calculator, right? I know what 3 times 3 times 3 is, right? I know what the fourth root of 81 is. Well, I had to think about that a little bit, but it's right, it's just 3. And then 3 cubed is 27. So either way, you get the same answer, right? Personally, I think this way is easier, but it's doable either way. Okay, so let's keep going. Let's do some more examples. Actually, before we get to the examples, let me remind you of the rules of exponents. These are rules of exponents. This was way back in chapter 5. From chapter 5, yep. So it's these rules here, right? If I have a to the power m times n, that's the same thing as a to the m to the power n, right? So don't get confused with a to the m plus n, which is a to the m times a to the n, right? That's a plus, right? And what happens if you subtract m minus n? Then you divide, right? This is a to the m divided by a to the n. Okay. And we also had these rules, right? And in fact, we used some of these earlier, right? If I have a to the negative n, that's just 1 over a to the n. If I have a times b all raised to the power n, this is a to the n times b to the n. And if I have a divided by b all to the power n, you can just do a to the n divided by b to the n. And there might have been a couple others. You know, for example, anything to the power 0 is just 1, as long as a is not 0. And remember here, b can't be 0. So b can't be 0, a can't be 0. Yep, a cannot be 0 here either. And a cannot be 0 here, right? So those are the rules for exponents, right? And up until now, well, just to remind you of what we did here, right? We had examples like this. If we have x to the power 4 times x to the power 3, by now you should know that this is x to the 7, not x to the 12, right? So this is 4 plus 3, right? This rule here. Just going the other way, of course, going backwards. And 4 plus 3 is 7, right? So this is x to the 7, not x to the 12. If you want x to the 12, you got to do x to the 4 to the power 3. That's x to the 4 times 3, which is x to the 12. So don't get those mixed up. It's a lot of people get these confused, so be careful. So we did this already. That was back in chapter 5. My point is that these m's and n's here, up until now, have been nice whole numbers. They could be negative numbers too, but they have to be integers. Now, this m and n can be rational numbers. These can be fractions. They can be rational numbers, right? Like 1/2 or 2/3. And so the same rules apply, right, whether m and n are integers or fractions. Right. So for example, suppose we want to simplify the following expression. Let's do y to the 2/3 times y to the 4/3. Okay. So what rule are we using here? We're using this one again, right? Y is a in this case, or a is y. M is 2/3 and n is 4/3. So according to this rule, this is just going to be y to the power 2 over 3. I need to write this a little bigger. So the exponent here is 2 over 3 plus 4 over 3. But what's that, right? Surely you know how to add fractions by now, especially when the denominators are equal. You just add the numerators, right? So this is 2 plus 4 all over 3. And 2 plus 4, of course, is 6. So this is 6 over 3. But 6 over 3 is 2. 6 divided by 3 is 2. So that's the answer, y to the 2, right? So all of this expression here, this is all just equal to y squared. Right. Yes. Yeah, do not leave your answer as this, right? 6 over 3, that's not in lowest terms, right? So always reduce your fractions. Make sense? Okay. So I think I'll do one or two more. And these are just rules of exponents. So suppose we want to simplify. So let's do a to the negative 2/5, and I'm going to write them, because they're small, I'll write them this way. A to the negative 2/5 times a to the 1/2, all of that raised to the power 3. And then we want to multiply by a to the power 5 over 4. Okay, and this is probably as hard as it's going to get, right? So let's just go step by step here, right? So notice inside here we're multiplying. So when you're multiplying, you just add the exponents here, right? So this is going to be, in parentheses, a to the power negative 2/5 plus 1/2. And we'll take care of this other stuff later. Okay, so what's negative 2/5 plus 1/2? In other words, what is this exponent here? Well, this is back to chapter 7 again, right? We can't add these fractions as they're written because they don't have the same denominator as they did here, right? See, here the denominators were both 3's, so that made it easy. Here, the denominators are not the same. So how can we add fractions when the denominators are not the same? Find your LCD, your least common denominator. In this case, 5 times 2. 5 times 2 is 10. Right? So what do I need to multiply by 5 to get 10? 5 times what is 10? 5 times 2 is 10. So multiply top and bottom by 2. 2 times what is 10? 2 times 5 is 10. See that? So the first fraction is just negative 4 over 10. And then the second fraction is 1 times 5 is 5 over 10. Now that I have the same denominator, right, I just add the numerators. That's a negative 4, right? You can think of this as, oops, negative 4, but now I got to erase the this thing here. Yep, you can do that. And then plus 5. So negative 4 plus 5, oops, is 5 minus 4, which is just 1. So this is just 1 over 10. Okay. So all of this is just this exponent here. Okay. So this is a to the power 1 over 10, oops, that's a 10, to the power 3 times a to the 5 over 4. Right? Okay, so now what's the next step? The next step is that we have a to the power 1/10 to the power 3. And you know what? I'm regretting writing this like this. Is this okay if I write it as a normal fraction? Again, it was okay, but I prefer this now. 1 over 10, right? Okay, so yeah, so effectively now what we're trying to calculate is all of this. And that to me looks like this rule way at the top here, right? See this? When you have an exponent to another exponent, you just multiply the exponents. So you're multiplying 1 over 10 times 3. And remember, this is 3 over 1. So I hope you don't have to do that over here. Right? When you multiply, you just multiply 1 times 3 is 3. 10 times 1 is 10. So the exponent here is just 3 over 10. Now we have to multiply by a to the power 5 over 4, and I'll write it this way again. Well, what rule is this? That's this rule here again, right? We got to add these exponents, right? So here we're going to add the exponents, right? The exponent 3 over 10 plus, sorry, that's a plus, 5 over 4. Now, again, the denominators do not match. So how can we add these fractions? Let's do that over here. Right? So 3 over 10 plus 5 over 4. So what's the LCD? Well, you could do 10 times 4 is 40. But because this contains a 2 and this contains a 2, right? This is 2 times 5 and this is 2 times 2. We only need 4 times 5. In other words, 20. So your LCD is 20. If you use 40, that's fine. You just have to simplify later. So we're going to use an LCD, least common denominator, of 20. Okay. Now, 10 times what is 20? Don't think too long. 10 times 2 is 20. So multiply by 2 over 2. 4 times what is 20? 4 times 5 is 20. Right? 20 divided by 4 is 5. Right? So now this becomes, hang on. Well, let's see. I'm running out of space here, so let me pull this down here now. Oops. Yep. So I get 6 over 20, right? Plus 5 times 5 is 25 over 20. And now that we have the same denominator, we just add the 6 plus the 25 all over 20, and that's going to be 31 over 20. Okay, so that's, oops, sorry about that. That's this exponent here, 31 over 20. Okay, now can we reduce that? Well, remember, 31 is a prime number, so even though we can factor the denominator, 31 is prime, so nothing cancels. So this is already in lowest terms. And so that's as simple as it gets, right? Again, if you prefer to write it with bigger numbers, you're welcome to write it this way as well, because the book will write it this way. I prefer to write it this way. Okay, so I think that's it for section 10.2. 10.2 is just getting used to exponents that are fractions, like 2/3, 4/3, even something as crazy as 31 over 20. That can be an exponent, right? Now, maybe we'll do one more here, right? How about if we convert this into a radical, right? Remember, how do you convert that to a radical? When you have a rational exponent, m over n, the n is the index, the m is the exponent, the power. So, yep, you could write this also as the 20th root of a to the power 31. Right? So that would be the same thing as a radical instead of an exponent. Now, how do you know not to do that, right? Why is this the answer and not the radical? Right? Why should you not do this? So the original question was to simplify. Right? Simplify means take this complicated expression, right? This was the original expression, and we did all this work and we simplified it, and we ended up with, right down here, this simple expression. So this has an exponent because these had exponents, right? The question did not say, right, the question said simplify. It did not say to convert to a radical. Right? If it did, yep, then this would be your answer because this is in radical form. Right? This is in exponent form. So because the question just said to simplify, right, we're just taking these exponents and rewriting them this way. It does not mean to convert to a radical. Okay? Okay.